Welcome to Brain Vision.
In this problem, we have two smooth billiard balls which have identical mass. Billiard ball A strikes B with a given velocity. We want to then find the final velocities of both balls after the collision. The x component of ball A we'll call VAX before the collision, we'll denote with subscript 1, is equal to minus 1.5 times the cosine of 40 degrees. And so we can immediately calculate this to be minus 1.1491 meters per second. We can also calculate its y component before the collision, VAY subscript 1. And this is minus 1.5 times the sine of 40 degrees. And this is equal to minus 0.9642 meters per second. So we have the x and y components of ball A's initial velocity. So we can see we've taken the right direction as positive, and we'll continue that and use the conservation of momentum before and after the collision in the horizontal direction. So the conservation of momentum tells us that the mass of A times VAX1, the initial momentum of A, plus the initial momentum of B, MB, VBX1, must equal to the final momentum after the collision, MA VAX2, subscript 2 is for after the collision, plus the momentum of B, MB, VBX2. So here we can substitute our values in, and we know the mass is 0.2 kgs, and we've got a minus sign for the velocity, which we calculated to be 1.1491, plus 0, since ball B is initially at rest, must equal to 0.2, the mass of A, times its final velocity in the x direction, VAX2, plus the mass of B, which is the same, multiplied by VBX2. So here we have an equation with two unknowns. So we need to set up another equation, and we'll use the coefficient of restitution to do this. So again, taking horizontal components, the coefficient of restitution, E, is equal to VAX2 minus VBX2 over the difference between the initial velocities in the x direction, VBX1 minus VAX1. And this coefficient of restitution E is given. So this is 0.85, which is VAX2 minus VBX2 over, since B is at rest initially, 1.1491. And so now we have two equations with the same two unknowns. So from our conservation of momentum and coefficient of restitution, we can solve these two equations simultaneously. And if we do that, we get the x component of A's velocity after the collision, VAX2, is minus 0.08618. We're keeping the decimal points for accuracy, that's meters per second. The x component of B after the collision, VBX2, is equal to minus 1.0629 meters per second. Remember, the minus sign means to the left. Now we'll look at the y components. Firstly, for A, if we use again the conservation of momentum, the y components of A, MA, VA, Y1 must equal the y component of the momentum after the collision, MA, VA, Y2. And this is because ball B only has horizontal momentum after the collision. And so we can simply see that VA, Y2, since the masses cancel, is equal to VA, Y1, which is 0.9642 meters per second. Now for B, we can do the same. And we're taking, so for A, we took the downward direction as positive, and for B, we can take the upward direction as positive. So MB, VB, Y1 must equal to MB, VB, Y2. And simply from here, we can see obviously that since B moves along the horizontal plane, its y component after the collision is 0. So from here, we can now find all our required values. So the velocity of B after the collision is equal to its x component purely. So that's VB x2, and this is equal to 1.06 meters per second to the left. VA2 is equal to, so the magnitude is the square root of the sum of squares of the components. So that's minus 0.08618 squared plus the y component 0.9642 squared. And so the magnitude of VA after the collision is 0.968 meters per second. And its direction, so that we can have the complete vector, theta A after the collision is equal to the arctan of the y component over the x component. That's the arctan of 0.08618 over 0.9642, and so the angle is 5.11 degrees, and that's from the positive y-axis.